Welcome to the course RF transceiver design. We are discussing the non-linearity in RF system, and we are at module 2 lecture 13. So, we will discuss RF transceiver design, non-linearity in RF transceiver design. So, in the last class what we have tried to derive the equation for IIP3. So, what exactly the IIP3 is? There is a first order term. So, this is a first order curve and there is a third order. So, why we are interested for only third order? Because the third order component, which is 2 omega 1 minus omega 2, 2 omega 2 minus omega 1 is coming to the is near to the our desired frequency that we are down converting. So, that is why third order is important, and that third order. So, this is a gain of third order which is increasing by 3 times, and this is a gain of first order which is increasing by single time. So, this when this both asymptotically will meet at one point, that point at input side is called as a input IIP3 and at output side it is called as a output IIP3. So, always because gain is involved, your output IIP3 OIP3 is equal to IIP3 plus gain. So, this is a gain of the system. So, if you would like to find the gain OIP3, that gain is added, otherwise the IIP3 is the point at which your first order and third order will intercept is called a third order IIP3. One more equation also that we have discussed, that if this is the first order component and if this is a first order component and if this is a third order component, when we are increasing the power of first order, the power of the third order is increasing 3 times. So, this is increasing 1 time and this is increasing 3 times. So, when you take a difference of this difference, when increment is happening, it is happening 2 times. So, that difference delta P can be given by 2 AIP3 minus A in 1. I can also represent in terms of IP3 in dBm, which is equal to P in plus delta by 2. So, this is widely used when there is a when we try to measure the IP3. So, I will just take one example. Let us say if your input power is around minus 70 dBm, means your 2 tone you have given, that is around minus 70 dBm, and let's say your delta F is around 1 megahertz. What is the delta F? The difference between the omega 1 and omega 2. So, omega 1, let us say certain frequency, then omega 2 will be omega 1 plus delta omega. So, this is a delta F, you can convert into the delta omega. So, omega 2 which is equal to omega 1 plus delta omega. So, you will have a 2 tone which amplitude you have given amplitude of minus 70 dBm to the amplifier, and in amplifier when you are getting, you will get certain output and it has a some third order component due to the non-linearity. You can find out 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1. So, you will get the power here, that is, let us say if this is minus 70 dBm and the gain of this amplifier is around 20 dB. So, you will get this is around minus 50 dBm, and if you have a third order term which is around minus 90, then the difference between these two is given by a 40. So, your delta P which is equal to 40. So, you can easily find out your IIP3 which is equal to P in, that is minus 70 plus 40 by 2, that is a 20. So, you can easily find out what is a IIP3 of your system if you know the difference between the first order and third order, and once you add the gain, it is a OIP3. So, this is by this method also we can find the IIP3 by using a spectrum analyzer. So, you can get the third order point and first order point. You can also use a network analyzer nowadays to sweep the power, and you can plot the IIP3 as well. So, this is how we can find out the IIP3. So, we will try to take another example also. So, if there is a LNA and if there is a two interferer, there are two interferer coming, and that is the frequency of this is 2.42 gigahertz and this is 2.43 gigahertz. So, and your desired signal is lying somewhere here at 2.41. So, what will happen? The third order component of this interferer will come to this desired frequency band. So, what we need to get is what IIP3 of this LNA, this is low noise amplifier, required if the IM product must. So, this IM product must remain 20 dB below the signal. So, for example, this interferer has a power of minus 30 dBm and this signal has an amplitude of minus 90 dBm, the power of minus 90 dBm. So, this is very small signal and there is a large interferer. So, what we are interested to find that what is a IIP3 required in the low noise amplifier. So, how can you proceed? We can use the same formula, that is we have used 20 log of alpha 1 input signal minus, that is a 20 dB, because we want it must remain below 20 dB, equal to the IIP3, that is a third order component, its amplitude is given by 20 log of 3 by 4 alpha 3 A intermodulation cube. So, we can again rewrite the same equation, 20 log alpha 1 A signal by 10, we take this term inside the log, 20 log of 3 by 4 A intermodulation cube. Then you will get alpha 1 A signal by 10 equal to 3 by 4 alpha 3 A interferer cube. So, you can write, we are interested to find the alpha 1 by alpha 3. So, that is alpha 1 by alpha 3, which is equal to 30 by 4 interferer cube by A signal. So, what you required is a amplitude of the interferer and amplitude of the signal in order to get the alpha by 3. So, you can convert easily minus 30 dBm to the amplitude that we have already seen by using the dBm to volt equation. You can also convert this minus 90 dBm. So, this you can convert into the equivalent voltage, and once you know the alpha 1 by alpha 3, you can find the IIP3, which is given by 4 by 3 alpha 1 by alpha 3. So, in order to find the requirement, you need to know that what kind of interferer is coming, and we already discussed when we are discussing basic of communication wireless communication, that all the standard will specify the blocker levels also, that how much blocker level you need to reject, and here interferer information is also provided in IEEE standard. So, when you are designing any receiver, you should prior know that what is the linearity that we are targeting. So, now the way we have done the cascaded, because in RF system, in RF receiver, there will not be only single component, there will be multiple component connected to each other, and the way we have find out the freeze formula for low noise amplifier means for noise figure. Similarly, we can also define the IAP3 of the complete system. So, for that we need to understand what will be the cascaded nonlinearity. So, if this is a xt in this term, if this is a xt and this is a first stage amplifier, or let us say any active component, it is a IAP3 1, and then the output of this is y1t, the second stage is a IAP3 2, and this is a y2t, that is the output. So, we will find out the y1t, what is so y1t. Same thing, we can use same equation, alpha 1 xt plus alpha 2 x square t plus alpha 3 x cube t, then y2 t. So, if its gain is denoted by alpha, the first stage, and this gain is denoted by beta, I can write beta 1 yt plus beta 2 y square t plus this is y1 beta 3 y1 cube t, because the output of first stage is input for the second stage. So, now we will expand the y2 t, which is equal to beta 1 alpha 1 x t plus alpha 2 x square t plus alpha 3 x cube t plus beta 2 alpha 1 x t plus alpha 2 x square t alpha 3 x cube t plus the square of this alpha 1 x t plus alpha 2 x square t alpha 3 x cube t whole cube. So, if we take the first order and third order term in this, you can write y2t. What are the first order term? Beta 1 alpha 1 xt, that is a first order. Then you will not find any other first order term, and there is a third order term that is given by the first third order term will be given by alpha 3 beta 1. So, this is this alpha 3 beta 1. Then you will get when 2 are multiplied, that is 2 alpha 1 alpha 2 beta 2 alpha 2 beta 2 plus alpha 1 cube beta 3, that is x cube t. So, the first term is coming from here. So, if I will note with the different color, the first term is coming from here, the second term is coming from this beta 2, and then this square is multiplied. So, alpha 1 alpha 2 x square into x square t into x t. So, that will be the second term, and third term is coming from beta 3 and this alpha 1 x cube. So, this is how you will get the 3 term means x cube for the x cube and for the xt. Then we already know what is the AIP3. AIP3 which is equal to square root of 4 by 3 alpha 1 by alpha 3. So, if for cascaded system the alpha 1 is written as a 4 by 3, that is beta 1 alpha 1 divided by alpha 3 beta 1 plus 2 alpha 1 alpha 2 beta 2 plus alpha 1 cube beta 3. If we will do the inverse of this, 1 by AIP3 which is equal to, you can write 3 by 4 alpha 3 beta 1 to alpha 1 alpha 2 beta 2 alpha 1 cube beta 3 by beta 1 into alpha 1. Then you will get, if we will do the square of this, means first we will find out alpha 3 by alpha 1 plus 2 alpha 2 beta 2 by beta 1 and then alpha 1 square beta 3 by beta 1. Now, if we take the square of this term, so then it can be written as a IIP 3 square, which is given by 3 by 4 alpha 3 by alpha 1 plus 2 alpha 2 beta 2 by beta 1 plus alpha 1 square beta 3 by beta 1. So, this is a mode. Now, this term is due to the second order. So, second order term, and because alpha 2 and beta 2 are a second order term, and that we can neglect if we are considering the third order linearity. So, this is due to the second order term and it can be neglected. So, you can write this equation as a 3 by 4 alpha 3 by alpha 1 plus alpha 1 square beta 3 by 4 beta 3 by beta 1. So, you can write this is the first stage nonlinearity, that is AIIP 3 1 square plus alpha 1 square by AIIP 3. This is a second stage nonlinearity. So, because for second stage the gain was a beta and for first stage gain was a alpha. So, the second order you can get this is due to the first order and this is due to the second order and the gain is multiplied. So, first order gain is multiplied. So, you can write, if you expand this term, you can write in terms of a square IIP 3 total is given by 1 upon a square IIP 3 of first stage plus alpha 1 square a square IIP 3 of second stage, then alpha 1 square, and here it is a beta 1 square by a square IIP3 third, and it will go on. You can also convert this into dBm. So, the square term will be reduced and the gain will be, so it can also be given 1 by IIP3 total is equal to 1 by IIP3 of first stage plus gain of first stage by IIP3 of second stage. Gain of first and second will be multiplied IIP3 of third stage, and it will go on. So, what this equation tells us that your IIP3 is mostly dominated by the last component. So, how much IIP3 your last component is adding, it will, so it will define that complete system IIP3, and it is always important that your last component in your receiver chain should be as linear as possible. And your in when we consider the noise figure, for that the first component is important. So, for receiver design, the for noise figure you should consider the first component, and for IIP3 you should consider the last component. But it is not always true, because we will also see one example that if you cascade the IIP3, but if your certain stage does not provide the sufficient IIP3, then your signal will be distorted. So, there are, let us say there is a first stage, this is a first stage and this is a second stage. And the first stage, let us say I have a, after when two tone I have applied, after the first stage I have a certain delta 1, means delta 1 means your first stage has a sufficient, means it has a non-linearity, and due to the non-linearity you will see the difference in the first order and third order, and that difference is given by delta 1. And when the same input is given to the second stage, you will have the difference of delta 2. So, when you have a cascaded system, and if there is a non-linearity in the first and second stage, so you should consider, so there are two possibility, that is your delta 1 is equal to delta 2, means when your IIP3 is almost equal. So, when delta 1 is equal to delta 2, then the IIP3 that is seen by the complete system will depend on the second stage. IIP3 is then there is another case when your delta 2 which is greater than delta 1. So, in that case also, because your delta 2 is greater than delta 1, but still because there is a difference already created by the first stage. So, the first your second stage will not add a non-linearity, but you will see the behavior of the first stage. So, your non-linearity of the first stage will be continue. So, your IIP3 is depend upon mostly the combination of first and second stage, and we should always avoid delta 2 which is less than delta 1, because here also, let us say if your preceding stage has a good linearity performance, but if your third stage, second stage has not the good linearity, then so here your delta 2 is less than delta 1, means this difference is less. So, your delta 2 is less than delta 1, then again IIP3 is depend upon second stage. So, this is a 3 cases where your delta 1 is equal to delta 2 is greater than delta 1 and delta 2 is less than delta 1. So, mostly in all the cases second stage is dominating, that is why and that is because of that equation that we have derived, that second stage is a dominating in the IIP 3. Now we have discussed about the noise figure and non-linearity. Now we will discuss the very important term for receiver, that is a sensitivity. So what is a sensitivity means? It is a minimum signal level that a receiver can detect with acceptable quality. So minimum signal, because at receiver you are going to get a very small weak signal and that we should detect. Currently our mobile can able to detect the signal which is around minus 100 to 110 dBm, which is coming around microvolt. So that is very small weak signal that a receiver can detect. So for sensitivity equation means definition, one more term that is important, that is with acceptable quality. This is we should emphasis. Let us say you can detect, but if it does not have acceptable quality, what it means, that it should have a sufficient SNR. It should have a sufficient SNR, and that SNR requirement is based on the, it is possible, it is depend upon modulated scheme or Shannon capacity theorem, your bandwidth of the system, the range that you have defined for your transmitter receiver. So your requirement of SNR is depend upon the multiple factors, but you should know that what is a sufficient SNR or what is the acceptable quality for receiving your signal. So when you define the sensitivity, always mention the acceptable quality, minimum signal level that a receiver can detect with acceptable quality, and it should have a sufficient SNR. So typically the SNR will range from 6 to 25 dB. So it is depend upon what is the next stage ADC and all requirement it has, and based on your baseband modulations that you have used. So all this is depend upon the SNR. Now we try to find out the equation for sensitivity. So SNR in, can I write the SNR in as a P signal by PRS? PRS is nothing but a noise power. P signal by PRS, and I will make sure SNR out, that is the output SNR, because here we are considering the sufficient SNR. Now what we are interested to get the minimum signal, means this is our important while defining the sensitivity, how much minimum signal level. So that is a P signal. So I can write down noise figure into SNR out into PRS. We can also write PRS into noise figure and PRS we have already defined when we have discussed the noise, and that is a KTB. So this will come as a KTB. So we can also write in terms of this is a KT, then bandwidth B, then so if we define the KT in terms of dBm, so the same received signal, if it convert into the dBm, it can be written as a minus 174 dBm per hertz. So this is a noise floor, means minus 174 dBm per hertz, and generally it has a bandwidth which is defined as a 10 log B multiplied, then you have a noise figure 10 log f, or you can also write NF and your SNR. So this is addition because we have converted into the dB. So I will rewrite the same. This is positive and SNR out. So this if you define the bandwidth of the system, then this is considered as a noise floor, and if you have a unity bandwidth, this is a minus 174 dBm per hertz, that is a KT noise, thermal noise. We are discussing the sensitivity, and here sensitivity we have already defined, that is minus 174 dBm per hertz into 10 log B. So if you just multiply the KTB, so this KTB is nothing but a thermal noise power, and that is also defined as a noise floor of the system. So instead of NF I will mention a noise floor of system, and then you have a noise figure and output SNR requirement is added. So this is what sensitivity means, and if we try to find out the we will take one example, it will help us to understand. Let us say there is a GSM standard. So if there is a GSM receiver, what is a SNR? Let us say SNR requirement is 12 dB. It is a 12 dB, not dBm, and your bandwidth is around 200 kilohertz. So what is a SNR? What is a sensitivity that, and if your noise figure of system is a 7 dB. So what is the sensitivity of receiver required? So that we can write P signal which is equal to minus 174 plus we should convert this 10 log into 200 K plus noise figure and the SNR output SNR that is required, that is a 12 dB. So it is around 12 dB. So roughly it will come around minus 102 dBm. So this much weak signal is coming to your GSM receiver, and you can also get the any receiver sensitivity. So what is the important term here is a output SNR that is required, the bandwidth of your system and your noise figure. So if let us say noise figure of your system is increasing, the amount of signal received will increase. So your sensitivity is increasing. So the level of sensitivity that you required, you cannot sense very weak signal if your noise figure is high. Again, if your bandwidth is high, you can your minimum signal requirement is increased. So right now by using a GSM, in this example GSM receiver can able to get the signal of the power minus 102 dBm. Same example here written. Okay. Now another important term for the receiver IP3 for let us say for receiver non-linearity is a dynamic range. So what it how you can define the dynamic range? It is defined as the maximum input level that a receiver can tolerate. divided by the minimum input level that it can detect. So, maximum input level that a receiver can tolerate, that is this, and minimum input level that it can detect. So, maximum and minimum term is given by sensitivity and maximum is given by the non-linearity. So, because your compression will compress the signal, so maximum is given by the uh, non-linearity. So, the difference between two is given by the dynamic range. It is called the dynamic range, and this is a compression based or a first order due to the first order non-linearity, because there is a compression will occur and this will maximum input level will limit. Now, there is another term, that is a spurious free dynamic range, that is written as a SFDR, spurious free dynamic range, and in that your maximum input level is defined by a second order, means intermodulation products, that is a third order nonlinearity. So, that is depend, your SFDR maximum level is depend upon the third order nonlinearity, and for dynamic range it is on the first order nonlinearity. So, always remember that noise defines the lower limit. So, that is why noise is important in your RF system, and interference and compression or nonlinearity defines the upper limit. So, your upper limit is always defined by the nonlinearity and lower limit is always defined by the sensitivity, and the difference between two is called as a dynamic range, or the much advanced term is a spurious free dynamic range. So, we will try to define the SFDR also. So, in the SFDR, the maximum relative level of the interference that a receiver can tolerate while producing an acceptable signal quality from a small input level. So, maximum relative level of interferers. So, here interferers, so more than one component that a receiver can tolerate. So, the maximum value while producing an acceptable signal quality, that means sensitivity of receiver from a small input level. So, we can derive the same. So, we can get P IIP3, this we already have defined, P in plus delta by 2. I can also write P in, this is nothing but P out, output power, minus P IM out, means intermodulation product out, that is the difference between this and this. This is a P IM out divided by 2. We can also, if we try to divide, if we consider P out which is equal to P in plus gain and P IM out equal to P IM in plus gain, and if we try to put this in this equation, we can also write the same equation, P in plus P in minus P IM in by 2. So, if you take 2 here, you will get 3 P in minus P IM in by 2, that is by 2. So, your input minimum means your maximum power P in 2 P IIP3 plus P IM in by 3. So, this is the upper limit. What is this? Due to the IM product, this is the upper limit of SFDR, upper limit of SFDR. And now we are finding the P I am in. So, P in max we can get the upper limit. What is I will just note it down here. The upper limit of SFDR is that value of P in which makes P I am in equal to integrated noise of receiver. So, we try to increase the power level, input power level, we increase the power level step by step, and the moment at which your power level is increased to level where your third order point will equal to the integral noise of the receiver. So, that will be defined as a upper limit of SFDR. So, what we can write P in max. So, we will write P in max which is equal to 2P IP3 plus what is this PIMIN. So, that is a lower limit, that is minus 174 plus noise figure plus 10 log B divided by 3. So, this is a P in max. So, what is the SFDR? So, in this equation, in this equation P I am in we have replaced with the minimum signal, that is a sensitivity of receiver, that is minus 174 plus NF by 10. So, this is a P in max minus we will divide the sensitivity. So, we will get the same thing 2P IP3 plus, let us say if this is KTB into noise figure. So, the minus we will just write minus 174 plus NF plus 10 log B divided by 3 minus. So, if I will make this term as a x, so sensitivity I can write x plus SNR out or minimum SNR that is required, SNR mean. So, again we can write 2P IP3 minus, so this is plus x and we can write minus 3x minus divide by 3 plus SNR mean. So, you can write 2 PIP3 minus 2x by 3 plus SNR mean. So, this x I can, if 2 by 3 we will take it out, this is PIP 3 minus 174 plus noise figure plus 10 log B and plus SNR mean. So, this is the final equation for SFDR, and for let us say for your system, this is a system noise. So, system noise power that is a if you have added the noise figure, that is nothing but system noise power. So, this can also be defined as a N naught, and we can also write this term as a 2 by 3 P IIP 3 minus N naught plus SNR mean. So, this is how SFDR is defined. So, what we try to understand, we have lower limit is defined by the sensitivity, and upper limit in dynamic range it is defined by the first order term, first order compression. But if it is more than one intermodulation product, then this is a third order and it is given by the it is written as SFDR. So, when your third order is increasing up to some level and your first order is increasing and your third order is equal to the sensitivity, that is the maximum input power, minus sensitivity will give you the SFDR. So, in this entire class we try to see the non-linearity, where we have defined the non-linearity, we have then gone through the cascaded non-linearity, dynamic range, we define the sensitivity of receiver, then dynamic range, and again SFDR. How so maximum level of input is defined by the interferer and the minimum is defined by the noise. So, thank you, and then now we have finished the basic of non-linearity. We will move forward in the next class. Thank you.